Good morning or good afternoon. Today I'm going to talk about uniform spaces in the point-free context. Uniform spaces were introduced in 1937 by André Weil. Uniform spaces are a notion which is more refined than the notion of topological space, but more general than the notion of metric space. A uniform space is more refined than a topological space in the sense that in a uniform space we can talk about 2 points being close to each other. However, this notion is less refined than that of a metric space, since here we cannot say that 2 points have a certain distance between each other. All we can say is whether 2 points are close to each other or not. Formally, a quasi-uniform space is a pair X cursive E, where X is a set and E is a collection of binary relations on that set. The elements of E are called entourages, and this is the French word that André Weil used in his original work, and it means roughly vicinity. For a vicinity R, we say that 2 points are close to each other if they are in that relation. And we say that 2 points are E close to each other. There exists a relation R in E such that X and Y are close. There is a natural way in which a quasi-uniform space induces a topological space. So we have a functor between the category of quasi-uniform spaces and the category of topological spaces, and this functor is essentially surjective. And intuitively this means that given any topological space, there always exists a quasi-uniform structure which is compatible with the topology of that space. Today we are going to be interested in 2 special properties that a quasi-uniform space might have. A quasi-uniform space is transitive when every entourage in E is a transitive relation, and it is totally bounded when for every entourage in E there exists a cover of the underlying set such that every element in that cover is R small. By R small, I mean that any 2 points in that set are R close to each other. We say that a transitive and totally bounded quasi-uniform space is a Pervin space, and Pervin spaces are going to be the main characters of this talk. There is a way of greatly simplifying the definition of Pervin space, and to do so we have to introduce a new notion. For a quasi-uniform space, a block is a subset of its underlying set, such that this relation that I'm going to write here now, such that this relation is an entourage in E. Blocks always form a sublattice of the power set of the underlying set of a quasi-uniform space, and Pervin spaces are special in that they are completely determined by their sublattice of blocks. And this is the fact that motivates the following definition of the category of Pervin spaces introduced by Jean-Éric Pen. So we define a new category called Pervin, where the objects are pairs X cursive S, where X is a set and S is a sublattice of its power set. Morphisms between Pervin spaces are functions between their underlying sets, such that the proimage preserves the property of being in the designated sublattice. So what is the precise sense in which this really captures everything that there is to know about Pervin spaces? Well, we have a full subcategory inclusion here of the transitive totally bounded quasi-uniform spaces into quasi-uniform spaces, and we have an equivalence of categories between the category of Pervin spaces and this category. These three categories all have point-free notions, point-free versions in the literature. We have the category of frames, the category of quasi-uniform frames, and the full subcategory of this determined by the transitive totally bounded quasi-uniform frames. And here we have the adjunctions, thanks to which we can regard the categories on the right as point-free versions of categories on the left. This is the classical adjunction that assigns its frame of opens to every topological space and the analog of a Zariski spectrum to each frame. And this is a variation in the quasi-uniform context of those two functors. So now we would like to have a category here which acts as a point-free version of the simplified version of the category of Pervin spaces. We define the category of Frith frames as follows. Its objects are pairs LS, where L is a frame and S is a generating sublattice. And when I say that S generates L, I mean that when we close S under arbitrary joins we get L. The morphisms in this category are frame maps such that they preserve the property of being in the generating sublattice. Indeed, we have two functors here, which are adaptations of these two functors to the quasi-uniform context, to the Pervin context. And as a side note, we note that in this point-free context we do not have any more an equivalence of categories, however we do have an adjunction. In the context of quasi-uniform spaces, a special role is played by the notion of completeness. Recall that a Cauchy filter in a metric space is a filter whose elements are arbitrarily small, and that a metric space is complete if and only if every Cauchy filter converges. We can translate both these notions in the quasi-uniform context, but keeping in mind that for a filter to be Cauchy, it means for a filter to contain arbitrarily small elements, in the sense that for every entourage in our quasi-uniformity there is a set which is small with respect to that entourage. So we are able to get a notion of complete Pervin space. We also have a point-free notion of completeness. In particular then, here we have the full subcategories of complete Pervin spaces and complete Frith frames. And along these two full inclusions, this adjunction restricts to an equivalence. We have the following theorem by Jean-Éric Pen, that a Pervin space is complete if and only if the topological space generated by it is sober, and if and only if both these conditions hold. I meant every element of S is compact in the topological spaces induced by this. We also have the point-free version of this theorem, which states the following. For every Frith frame LS, this is complete if and only if L is isomorphic to the ideal completion of S. So every complete Frith frame is uniquely determined by its lattice component. This is the intuitive explanation of the fact that we have an equivalence of categories between the category of complete Frith frames and the category of distributed lattices, and this equivalence is given by this forgetful functor. A little less trivial is the equivalence that we have between complete Pervin spaces and Priestley spaces. Recall that in 1972, Hilary Priestley famously proved that these two categories are actually equivalent. And we have that the top square in this diagram commutes, so that Priestley duality is in this sense equivalent to the duality between complete Pervin spaces and complete Frith frames. This suggests that it is very natural to see Priestley duality as a duality in the quasi-uniform context, and in particular in the Pervin context. Notice that Priestley duality can be seen as the restriction of this duality along full subcategory inclusions, whereas it is not possible to see Priestley duality as a restriction of this more classical duality along full subcategory inclusions. If we wish to see it as a restriction of this, we have to restrict the morphisms too. And this was the end of my talk, so thank you for your attention.